Okay, assalamu alaikum everyone. Let's begin then. So we covered the concepts of momentum in the last session, and today what we want to do is we want to do some more practice in that first of all, and then after that, if there are any other problems, any other questions from any of the other topics, we could also have a look at a couple of those questions as well. Okay, so that's the plan for today's class. Now, first of all, let me know the questions that you have from the momentum worksheet. If there are any problems from that, we could start from those problems first of all. So let me know the questions that you have from the momentum worksheet first of all. Any questions from the momentum worksheet? Okay. So whatever messages you posted earlier, can you please post them again? I think I joined from the other device late, so I can't see them on my other device. Can you please copy and paste them again? Okay, question 9, question 10. All right. Sure, let's start with that. Okay, Jenny, let's get started. So let's start with some momentum questions. First of all, this is question number 9 from the worksheet. We're starting from this. It says 3 particles P, Q, and R of masses 0.1 kilograms, 0.2 kilograms, and 0.5 kilograms respectively. They are at rest in a straight line on a smooth horizontal plane. So initially, all of them are at rest. Okay. Particle P is projected towards Q at a speed of 5 meters per second. So that's the first thing that's happening. And then they're saying after P and Q collide, P rebounds with speed 1 meter per second. So after they collide, P rebounds with speed 1 meter per second. Find the speed of Q immediately after the collision with P. Now, the first part seems fairly straightforward. It's a simple application of conservation of momentum. So what we can do is we can represent this situation in a diagram like this that helps with understanding. We've got particle P. Let's say this is particle P. We have another particle Q, and we have another particle R. We've got their masses given 0.1 kilogram, 0.2 kilograms, and 0.5 kilograms. Initially, they are at rest, and now what's happening is P is projected towards Q. So P is projected towards Q at a speed of 5 meters per second. So P is going towards the right side at a speed of 5 meters per second. Now, this is what's happening before collision. So I'm going to write that here. Before collision, P is moving to the right at 5 meters per second, and Q is at rest. So that's at 0 meter per second. What happens after collision? After the collision happens, we are given that P rebounds with speed 1 meter per second. That means P after collision starts moving towards the left side at 1 meter per second. Okay. And what we have to find is, we have to find the speed of Q immediately after collision. This is what we're looking for, VQ. That's what you want to find out. Okay. Now, R, that's at rest. It was at rest before the collision. It's at rest after the collision as well. There's nothing that's changing with R. So we don't have to worry about that. Just apply conservation of momentum on particles P and Q. Let's just focus on them. R was at rest and it remains at rest. So we can just ignore that for this first collision. So we can say momentum before collision, that should equal momentum after collision. What's the momentum before collision? Remember, in momentum, we have to consider one direction positive throughout the journey. We have to consider one side positive throughout the journey. So let's say we consider the right side positive. If the right side is positive, you can say the momentum of P before collision, what is that going to be? Mass of P, which is 0.1, into velocity of P, which is 5, plus mass of Q, which is 0.2, into velocity of Q, that's a 0. That's the momentum before collision. That equals momentum after collision. Momentum after collision, mass of P, that's 0.1, into velocity of P. You see, this is moving towards the left side. We took right side as positive direction. This velocity is going to be -1. Okay, so be careful about the sign here. And then plus 0.2 VQ, and that's going to give us the velocity of VQ after collision. That's it. We just solve this equation. This gives us 0.5 equals minus 0.1 plus 0.2 VQ, 0.6 equals 0.2 VQ, and the velocity of Q after collision, it turns out to be 3 meters per second. Okay, so for the first part was fairly straightforward, just a simple application of conservation of momentum. Okay, that was part A. Now it says Q now collides with R. Okay, so after this first collision happens, now Q collides with R. Immediately after this collision, R begins to move with speed V meter per second. Given that there is no subsequent collision between P and Q, find the greatest possible value of V. That's what you want to figure out. Okay, now how exactly do we think about this? Greatest possible value of V. What I'm going to do is I'm just going to represent those three particles here again, and let's write down their velocities, and that will help us understand this better. So now we're talking about second collision. Okay, we're talking about second collision. Q is colliding with R. Okay, so I'm just going to edit this a bit now. Okay, so the first collision has already happened. The first collision has already happened. Okay, and in that first collision, after that first collision, we know that P is moving towards the left side at 1 meter per second. So that's the current state right now for the particle P. It's moving towards the left side at 1 meter per second. So we're talking about what's happening after the first collision, okay? So P is moving towards left at 1 meter per second. What about Q? We found the speed of Q, 3 meters per second. Q is moving towards the right side at 3 meters per second. Okay. And what about R? R was at rest. This is the situation before the second collision now. Okay. Now what happens is Q and R, these two particles, they collide with each other. There's a collision between Q and R. Okay, there's a collision between Q and R. Now, immediately after this collision, R begins to move with speed V meters per second. So the speed of R after collision is V meter per second. Let's write that down, V meter per second. Now, which direction is it going to be in? Is it going to be towards the right side or towards the left side? Can we know that? Is there a way to know that? You see, R was at rest. R was at rest. Q is hitting R from the left side, right? The only possibility is that R begins moving in the right direction, right? It can't be that Q is hitting it from the left side and R moves towards the left side because of that. That would not make sense, right? So the only possibility is that the movement of r is towards the right side. Okay, so it has to be towards the right side. Okay, we have to find out the greatest possible value of v given that there is no subsequent collision between p and q. No subsequent collision between p and q. Where are the particles p and q? P was moving at 1 meters per second to the left. After collision, q would have some speed, right? It could be moving towards right, it could be moving towards left. They are saying p and q, they do not collide after collision. So do we know the speed of p after collision? Velocity of p after collision? P is not colliding with anything, right? So whatever was its velocity before the second collision, it remains the same. So P is still moving at 1 meter per second towards the left side. P is still moving at 1 meter per second towards the left side. What's the greatest possible value of V such that Q and P, they do not have any subsequent collision? That is what we want to figure out. Now, when will they have any collision? Can we think about that? Let's think about that. Let's suppose Q is moving towards the right side at any velocity. Okay, let's say Q after the second collision starts moving towards the right. Now, can P and Q collide in this situation? P is moving towards left, Q moves towards right. That means they're not going to collide. So if Q is moving towards the right side, then there can be no collision. Okay. What if Q is moving towards left? If Q is moving towards the left side, I'm just writing a random number. Let's say Q started moving towards the left side at, let's suppose, 2.5 meter per second. Now, in this case, will there be any collision between P and Q? P was moving at 1 meter per second. If Q is moving at 2.5 meter per second, at some point, Q is going to catch up with P and there will be a collision. If it was, let's say, 0.5, in that case, it's not going to catch up, right? Because P will be moving faster, Q will be moving slower. What is that cutoff point? What is that a critical point at which if the velocity of Q was to even slightly increase, there will be a collision? Let's think about that. If Q was moving at 1 meter per second, let's say, towards the left side. If Q was moving towards the left side at 1 meter per second, will there be a collision in this case? If it starts moving towards the left side at 1 meter per second, P is also moving at 1 meter per second, Q is also moving at 1 meter per second. They will not collide in this case, right? Because they're both moving at the same speed towards left. But if this velocity was to even increase by a small fraction, if this velocity was to increase even by a small fraction, there will be another collision between P and Q in that case. So the cutoff point that we have is when Q, its velocity is 1 meter per second towards the left side. That is going to give you the extreme value for V. So that's what we consider. We say, let's find this value of V when Q is moving towards the left side at 1 meter per second. In this case, if we were to apply conservation of momentum on these two particles, what would we get from that? Momentum before collision, that should equal momentum after collision. What's the momentum before collision? Momentum of Q, that is 0.2 into 3, plus momentum of R, that's 0.5 into 0. That equals momentum of Q after collision, which is 0.2 into -1 plus 0.5 into V, which is the momentum for R. Let's simplify this. We get 0.6 equals minus 0.2 plus 0.5 V. and that gives us 0.8 over 0.5, and the value of V turns out to be 1.6 meters per second. This is the value for V. This is the value for V, the greatest possible value for V, such that there is no further collision between P and Q. Okay, now that we have this value, let's think about this again. You see momentum before collision, what was that? 0.6. That's a fixed value. Momentum before collision, there's nothing that we do not know before collision. We know the velocity for Q, we know the velocity for R. So momentum before collision has to be 0.6. So momentum after collision, this also should add up to 0.6. If this value of V was to be even slightly bigger than 1.6, so if the momentum for R was to be greater than this, when would it be greater? When would it be greater? It would be greater if V was to be more than 1.6. Then if this increases, since the total has to be 0.6, this minus 0.2 will have to be an even smaller value, a more negative value. And for that to be a more negative value, this velocity will have to be greater than 1 towards the left side, and there would end up being collision, right? So momentum, since momentum after collision is fixed at 0.6, if we increase the velocity of R towards the right side to balance that, the velocity of Q towards the left side would have to be bigger as well, and there would end up being a collision. Since the maximum velocity of Q towards the left side can only be 1, that gives us the maximum velocity of V towards the right side, and that velocity is 1.6. That's what we were looking for. That's the maximum, the greatest possible value V that we get, 1.6 meter per second. What if Q comes to rest? Then there's no collision. If Q comes to rest, that would mean that it's at 0 meter per second. P is moving towards the left side at 1 meter per second. There would be no collision. So the extreme point is at which the decision between there being a collision and there not being a collision, when that changes, that is this particular value, 1 meter per second, right? If it's any less than 1 meter per second towards the left side, there will be no collision. If it's more than 1 meter per second towards the left side, there will be collision. So this is the cutoff point that we've got. Okay, this is the cutoff point that we have. We find the corresponding value for V for that. Why would we consider them one object? Do they tell us anywhere in the problem here that they correlate or something? Why would we consider them one object? It doesn't say that anywhere in the question. Why should we consider that one object? Is there any reason to believe that? Yeah, so the question doesn't mention anything like that. So we don't consider them a single object. They're still separate objects. So no, they're not considered one object. Any other problem? Does this make sense? Is this clear to everyone? Yes? No? Any responses? Okay, good. All right, that was question number 9 from the worksheet. This was a slightly tricky one. The second part of this, understanding how to formulate that situation. Let's have a look at this question now. Question number 10 from the worksheet. Okay, question number 10 from the worksheet. Let's try this now. It says particle A is projected vertically upwards from level ground with an initial speed of 30 meters per second. At the same instant, the particle B is released from rest 15 meters vertically above O, the mass of one of the particles is twice the mass of the other particle. During the subsequent motion, A and B collide and coalesce. So now they're saying they coalesce, they merge, they combine to become one object. We need to find the difference between the two possible times at which C hits the ground. Okay? At which C hits the ground. Now, this is one of the more difficult questions that you'll find on momentum in the recent papers. In fact, this I remember, this is from a paper that had a threshold. I think I was mentioning that in one of the M1 past paper session as well. This is from a paper that had a threshold of 28 out of 50 for an A, because this was a fairly difficult question. It was, and there was like at least one other question that was fairly tricky, and this paper was almost impossible to complete in time. It was an extremely lengthy paper because of some other long questions in that as well. So it's very unlikely that anyone got the full paper correct, or anyone even was able to attempt the full paper. That's why the threshold ended up being so low for this paper. It was only 28 out of 50 for an A. So it's a fairly difficult problem. And it's, again, that type of problem that I was mentioning yesterday, when you have momentum coming with kinematics. Momentum and kinematics, when they come together, these questions tend to be quite complicated. We were doing one from March 24 yesterday as well, March 24, paper 4.2. That was also another very similar question. Kinematics and momentum together took very, very long. And you'll find a number of such questions in recent papers, which make those papers quite lengthy. And this is actually the reason why recent M1 papers have started becoming very lengthy, which did not used to be the case earlier. Let's have a look at this now. A particle A is projected vertically upwards from level ground with an initial speed of 30 meters per second. Okay, let's represent it on this diagram. We have this horizontal ground, and a particle is projected at an initial speed of 30 meters per second. So this is how you're projecting it. At the same instant, there's another particle B that is released from rest 15 meters above this point O. This was A. In fact, this is A. It's projected vertically upwards. And there's another particle on top here, let's say here. This is named B. It's released from rest at the same instant. So its initial speed, its initial velocity is 0 meter per second. It's released from rest from there. And we know that the distance between these two particles initially, that is 15 meters. B is 15 meters vertically above A. The mass of one of the particles is twice the mass of the other particle. Do we know which particle is twice the mass of the other particle? They don't mention that, right? They don't mention which particle is twice the mass of the other particle. So we would have to consider two cases for this. It could be that mass of A is twice the mass of B, or it could be that the mass of B is twice the mass of A, right? Both possibilities are there. So we might have to make two cases. We'll come to that. During the subsequent motion, A and B collide and coalesce to form particle C. Now, as B is moving downwards and A is moving upwards, they collide at some point, okay? We don't know where that point is. We don't assume that that's the midpoint, okay? You can't say that they meet exactly at the 7.5 meter mark. No, that's an assumption. It could be anywhere, okay? So let's mark at some point randomly. Let's say they collide at this point here. Let's call this point X. So what happens is B moves down by a certain distance. Let's call that the distance, the displacement of B. Let's call that SP. And A moves up by a certain distance. Let's call that the displacement for A. And at this point X, what happens is they collide with each other. And at this point, they coalesce. They coalesce, that means they merge to become a single object. And this merged object, C, it goes down and hits the ground. And we have to find the time, the difference between the two possible times. So that's where this thing is going to come in. one mass is twice the mass of the other. So we'll have to consider two cases. That's where the two possible times are going to come from. We have to find the difference between those two possible times. Now, there are different parts of this journey. Let's break them down. There are different parts of this journey. Number one, when B is moving downwards, A is moving upwards before collision until they reach that point X. That's the first part of the journey. Okay. And then collision happens. When collision happens, we would have to use conservation of momentum, right? To find the velocity after collision. We'll have to use conservation of momentum for that. And then once they merge with each other, then that combined particle, that will go and hit the ground. That's the third part of the journey. So you have to break it down into parts like this. Let's consider the first part first of all, before collision, and see what's happening in that part of the journey. So the first part of the journey is when you have A moving upwards and B moving downwards. So that's where kinematics concepts have to be used, right? There's no collision for this point for now. A is moving upwards, so what we can do is we can take upwards direction for A positive. B is moving downwards, we can take downwards direction for B positive. What do we know about both the particles? For A, what's the initial velocity? For A, the initial velocity is 30 meters per second. We say U is equal to 30. All right. And what about acceleration? We are taking upwards positive. Acceleration, gravity acts downwards. So acceleration is going to be -10, right? What else? Do we have any other information? No. Okay, let's write it down for B as well. B is moving downwards. We take downwards direction positive for B. The initial velocity for B is 0. And what else? Acceleration. It's also free fall. Acceleration for B is going to be +10 because we're taking downwards direction positive for B. Gravity is also acting downwards. Acceleration is +10. Okay. Now, these are two values that we know for each of them. Do we have any other information? We don't have final velocity, time, displacement. So now we need to figure out those quantities that are common between them, that we can use to connect these two objects. What about time? They both started at the same instant, right? We know that they both started at the same instant. So time is going to be common between them. So time is a common variable. We can use time as another variable. You can say if time for A is t, then the time taken for B to reach that point X, that's also t. So time is common between them because they started at the same time instant, and until the point of collision, it would take the same time for both of them. That's why they're colliding. They're reaching that same point at the same time instant. What else? Do we have any other information that we can use to connect these two? We are given the total displacement. The total displacement was 15 meters. So what that means is B is moving some distance in the downward direction. A is moving some distance in the upwards direction. At the point X, they meet each other. What's the total going to be for both of these displacements? If I were to add SA and SB, their sum is going to be 15. The sum is going to be 15. Okay. So that's the way to connect these two equations. We can say SA plus SB, that is going to be equal to 15. That's going to be equal to 15. Okay. And now, which equation can be used to connect these four quantities, S, U, A, and T? S equals UT plus half AT square. For A, we can say U, which is 30 into T plus half into A, which is -10 into T squared. That's the displacement for A. Plus displacement for B, initial velocity is 0 into time plus half into A, which is 10 into T squared. That's the displacement for B. Their sum has to be 15. And solving this equation can give us the value for T until that point of collision. All right. Let's solve this equation and see what that gives us. 30T minus 5T squared plus 5T squared equals 15. And the value that we get from that, is 15 over 30 is 0.5. Okay, so that tells us that the collision happens when time is equal to 0.5. Collision happens when time is equal to 0.5. We are taking upwards positive for A, downwards positive for B. A was moving in the upwards direction, so that's what we do in kinematics generally. We take upwards positive for A because that was projected in the upwards direction. B was moving downwards, we took downwards positive for B. So keep that in mind. That's why the velocities are going to be positive for both of them, but acceleration for the first one is going to be negative, and for this it's going to be positive, because when we take upwards positive, gravity is acting downwards. So this is negative. When we take downwards positive, gravity is also acting downwards, and we're taking downwards positive. In that case, acceleration is positive 10. Okay, so we got the value for t. For the instant, until the instant when they collide with each other. Okay, what happens at this point now? The collision happens and they coalesce to become a single object. So now we need to figure out what happens during collision. So we need to use conservation of momentum. Conservation of momentum requires the velocities before collision, velocities after collision. So we need the velocity for A and B just before the collision happens. Okay, we need the velocity for A and B just before collision happens. How do we get that velocity? For A, we can, so in fact, for both of them, we can use V equals U plus AT. VA equals U plus AT. U is 30 plus A, that becomes minus 10 into T, which is 0.5. Now this gives us 25 meters per second. And similarly for B, V equals U plus AT. We are talking about final velocity for their journey from this point to this point until they reach X. Okay. Velocity of B, U plus AT, 0 plus 10 times 0.5, and that turns out to be 5 meters per second. So A is moving upwards. A is moving upwards at 25 meters per second, and B is moving downwards at 5 meters per second just before collision. That's what we know. Okay, just before collision, A is moving upwards at 25 meters per second, and B is moving downwards at 5 meters per second. That's what we know. So these are velocities just before collision. Let me write that down here. Velocities of A and B just before collision. So now what we can do is we can apply conservation of momentum. Now we can apply conservation of momentum and see what that gives us. Okay, now let me represent that in the side. A is moving upwards. A is moving upwards. And B is moving downwards, right? That's what's happening. Before collision, we know that B is moving downwards at 25 meters per second. And A is moving upwards at 5 meters per second. Or is it the other way around? A is moving upwards at 25. Okay, so it's the other way around, I'm sorry. A is moving upwards at 25 meters per second, and B is moving at 5 meters per second in the downward direction. That's the situation before collision. What happens after collision? What happens after collision? After collision, A and B coalesce, and they become one single object. That's what they're saying. It becomes one single object, particle C. So after collision, we have one particle, that's particle C. We don't know what its velocity is. Let's just call that VC, velocity of C. And we need to apply conservation of momentum on this now. How do we do that? Momentum before collision equals momentum after collision. But now we've got a problem. And the problem is we don't have the masses given for these objects. We don't know the mass of A. We do not know the mass of B. That's not given. They did not tell us that. The only thing that they told us was that mass of one of the particles is twice the mass of the other particle. Now, which one is twice the other? We don't know, right? It could be that A's mass is bigger, or it could be that B's mass is bigger. So what we do is we consider two cases for this. Case one, that the mass of A, let's say that's M, and the mass of B then would be 2M. That's one possibility. Like if A is M, B is 2M. Then what about the mass of C? That's the combined particle. That will be the sum of both of them. That will be M plus 2M, sorry. That is 3M. That's case one. And the second possibility would be that mass of A is 2 times M and mass of B is M. And then the mass of C, that's the sum of both of them, that still remains 3M. These are the two cases that we consider, because in conservation of momentum, we need the mass as well, right? In kinematics, we did not need that. So we did not do anything for kinematics as far as making the cases was concerned. We just considered one single case because mass did not have anything to do with these calculations. But in conservation of momentum, we also have mass in the formula. So we would have to consider the two cases like this. And now in the first case, if we apply conservation of momentum here, let's see what we get from that. Momentum before collision. Mass of A, that is M, times the velocity of A, that's 25. Now we have to consider one direction positive. Let's consider upwards positive, let's say. Remember, in conservation of momentum, we have to consider the same direction positive for all objects. In conservation of momentum, we have to consider the same direction positive for all objects. So we consider, let's say, upwards positive. If we consider upwards positive, the velocity for A is going to be 25. What about the velocity of B? That would be -5 because that's moving in the downward direction. That equals mass of C, which is 3M times the velocity of C, that's VC. Now let's simplify this. This gives us 25M minus 10M equals 3M VC, 15M equals 3M VC, and the velocity of C, the combined particle, that turns out to be 5 meters per second from this. That's the velocity of the combined particle, 5 meters per second. It's turning out to be a positive value. That means the combined particle after this collision is actually moving in the upwards direction, right? It's positive. We considered upwards direction positive. So the combined particle, it's moving in the upwards direction, right? So when they collide here, the combined particle will go up and then it will go down after that collision, right? Because A had more impact. So because of that, the combined particle actually starts moving upwards after collision. All right, that's case one. What happens in case two? In case two, the mass of A is twice the mass of B now. Okay. Mass of A, that's 2M, times the velocity of A, that's 25, plus mass of B, that's M, into velocity of B, that's 5 meters per second, and minus 5 meters per second. That equals 3M into VC. Let's solve this now. 50M minus 5M equals 3M VC, and 45M equals 3M VC. The value of VC here turns out to be 15 meters per second. Again, it's also a positive value. That means the combined particle in the second case is also moving in the upwards direction. Okay, so now the collision has happened. After that collision, the combined particle, depending on which mass is bigger, whether A's mass is bigger or B's mass is bigger, it either starts moving in the upwards direction at 5 meters per second, or it starts moving at 15 meters per second in the upwards direction, One of these two things happens. Now, in both of these cases, they are saying, find the difference between the two possible times at which C hits the ground, at which this combined particle hits the ground. So find the time taken for this combined particle to hit the ground for each of those cases and find their difference. Okay? All right. Now, let's look at the first case. So after the collision has happened, let's say this is the combined particle C. Now we know that C starts moving in the upwards direction at 5 meters per second. And now at some point it's going to start coming down, right? So it goes up for a while and then it will go down like this. And it's going to hit the ground at some point. Let's draw that here. This is horizontal ground. This is particle C. It starts moving in the upwards direction at 5 meters per second after that collision. And then at some point, it's going to go down and hit the ground. Okay, that's what happens. Okay. Now, what do we know about this journey? Now, it's again kinematics. It's again free fall. We have some initial velocity. We have the acceleration. We have to use those quantities to find the time that this combined particle takes now to hit the ground. Okay. What do we know about this particle now? It starts moving in the upwards direction. It's two-way motion. What do we do in such cases? We consider upwards direction positive. So let's say upwards is positive. What information do we have about this? We again use constant acceleration formulas. It's free fall. We know the initial velocity, that's 5. We know the acceleration. If you're taking upwards positive, what about acceleration? Acceleration would be -10. What we're looking for is time. That's what you want to find out. Do we know final velocity? Do we know displacement? We don't know any of those things. Is there a way to find any of those things? Displacement or final velocity? Can we say anything about them? Displacement or final velocity? Let's go back to that original diagram. Remember what was happening? A was going upwards, B was going downwards, and they collided at this point X. That was the point of collision. Point X was the point of collision. Now, this is where they merge to become object C. So the height of C, the height that C has at this point, this height is basically whatever was the height of X, the point of collision, right? This point is X, the point of collision. We can use that to figure out how much displacement C would have from this point until it reaches the ground. How can we do that? A traveled from the ground to that point X. How much displacement did it travel? What is that represented by? That displacement is represented by SA here. If we can find the value of SA, that will give us the height of this point of collision above ground. Okay, so we can find that using that initial set of values that we had for A. For A, we knew that initial velocity was 30. Acceleration was -10. We also found the value for time for this. That turned out to be 0.5. So what we can do is we can find SA from that. Let's do that calculation here. SA, what would that be? UT, U is 30, into T, which is 0.5, plus half into A, which is -10, into T squared, which is 0.5 squared. So I'm using this equation, S equals UT plus half AT squared. That will give you the point, the height of the point X, the point of collision. Let's see what this turns out to be. Can somebody do this calculation quickly? 15 minus 5 times 0.25. What do you get from this? 13.75. Okay, thank you. 17.75, that's the displacement that we get from this. SA. Okay. Now, what is this telling you? This is telling you the height of the point of collision above ground. Height of the point of collision. All right, 13.75. Now, let's go back to that situation. So C started from this point. We know that this height is how much? 13.75 now. That's the point of collision. Its height was 13.75. Now, after collision, what happens is C goes upwards for some time, and then it goes down. What's the displacement for C? Considering that upwards direction is positive, can we say anything about displacement of C? What is the displacement of C going to be? Can everyone write that value in the chat? What do you think? What's the displacement of C going to be from its current position at X until it reaches the ground? What is the displacement going to be? If the height of that point is 13.75, what's the displacement value? What does displacement represent? It's the shortest distance from the starting point to the end point, right? Starting point was X, and the particle is going towards the ground. This is the shortest distance. It's 13.75. But since we are saying upwards is positive, it's in the downward direction. The value for displacement is going to be minus 13.75. That's the value for displacement. And now we can use this equation, these four things, to find the time that it takes for C to hit the ground. Which equation do we use here? S equals ut plus half at square. And that gives us minus 13.75. That equals 5 times t plus 1 over 2 into a, which is minus 10 into t squared. And that will give it the value for t. Let's see what this turns out to be. Minus 13.75 equals 5t minus 5t squared. So if all of that was not enough, now they want you to solve a quadratic equation as well. 5t squared minus 5t minus 13.75 equals 0. How do we solve this? We put these values in the quadratic formula. Minus into minus 5 plus minus square root of minus 5 whole squared minus 4 into 5 into minus 13.75 whole divided by 2 times a, 2 times 5. And that's going to give you the value. You can see what that is. What's the value of t that we get? What value of t do we get? Okay, so one value of t that we're getting is 2.232. Okay, and the other value of t that we're getting is negative 1.232. Now, of course, negative value is not possible. This is one value of t that we're getting. 2.232. Okay. All right. Now, this is for one case. This is just for one case in which mass of B was twice the mass of A. Now we do exactly the same thing for the second case as well. Okay. So we have to do all of that all over again for the second case as well. What I'll do is I'll just copy this, which unfortunately you cannot do in your exam. So you have to do this working. This is the second case. In the second case, you see the combined particle was moving at 15 meters per second now. So what happens is now the initial velocity is 15 meters per second. Everything else is the same as before. So all that changes is initial velocity now changes to 15. This is now 15. So in the equation as well, instead of 5 being the initial velocity, we've got 15. So we've got 15 here. And we have 15 here. And it's also minus 15t. And this is minus 15 squared. And that will give you another value for t. You can see what that turns out to be. So we just replaced 5 with 15 there. The initial velocity, instead of being 5, now it's 15. Let's input this in the quadratic formula. 5 minus 15 and minus 13.75, and this is giving us time equals 3.736, and the other value will be negative, that's minus 0.736. So one possible time for C to hit the ground is 2.232, and the other is 3.736. 0.5 seconds had already passed initially for both of them, so for the difference, it does not matter. We can just find the difference between these two values now and see what that turns out to be. The difference in these two values, that's 3.736 minus 2.232, and that will give you the result. You can see what that is. 3.736 minus 2.232. And that gives us 1.504. To three significant figures, that would be 1.50. That's the difference between the two possible times that C hits the ground. When C hits the ground. Does that make sense? So just this much working for 8 marks. Now, how would you do well in this paper? By making sure that you do not do a question like this in the middle of the exam, because that is what is going to ruin your paper. If you end up getting stuck at this question in the middle of the exam, you need to make sure that all the questions that you do know about, you do those questions first, so that any question like this, it's left for the end. And then if you are prepared well, if you're finding something difficult, hopefully everyone else would be finding that difficult as well, and the threshold will take care of it, which in this paper, it did. So only those people would have suffered who ended up trying this question in the middle of the paper, and because of this, some other question, they ended up losing marks in, because maybe they panicked at the end, they did not have enough time left for that, or they ended up just missing some part. That is when the problem is going to be. So just make sure not to get stuck in the middle of the paper, and the rest will take care of it. Should we always attempt momentum question at last? No. A lot of times momentum questions are easy as well. So when momentum comes along with kinematics, that is something that I would recommend that you do it towards the end, that you do that towards the end. That ends up taking a lot of time generally. So kinematics and momentum, when they come together, and it's a big question, I would say generally you avoid that in the middle of the exam. But otherwise, if it's not kinematics and momentum both in the same question, then the momentum question is going to be one of the easiest on the paper as well sometimes. So you have to decide based on that. Yes, recent papers are much more difficult than, you can say, the older papers. They, in the last few years, they have started to increase the difficulty level, and the M1 papers have become lengthier as well. Okay, there's no specific pattern as such that is there for the recent papers. They haven't changed the pattern. It's the same 6 to 8 questions that you get. They have stated now that the questions are not necessarily going to be in the increasing order of marks. Earlier, it used to be that they used to have shorter questions in the beginning, and then gradually they used to increase marks. Now it's kind of random, but still you will find the most difficult questions are towards the end. The 6th and 7th question, generally they are the more difficult ones. Okay, but sometimes it is possible that one of those later questions is easier as well. So you need to make sure that you go through the paper twice. In the first go, you do the easier questions, the easier parts, making sure that you get all the marks on the questions and the question parts that you do know about. And then the questions that you do not get in the first go, then you attempt them in the second go. And that should be fine, inshallah. If you're prepared well and you cannot figure something out, that hopefully means that others are finding that difficult as well, and threshold will take care of that. Okay. In S1, normally there isn't much issue of time. If you practice S1 enough, uh, you won't generally have a time problem in S1. That's not a lengthy paper generally. Some questions require some thinking time, yes, but most questions have very little working required. Yes, paper three and M1, yeah, paper three and M1, they tend to be the lengthier papers. They are both uh, pretty long. You just need to make sure that you practice a lot. That will increase your speed. So you save time on the easier questions so that you have more time left for the more difficult questions towards the end of the paper. That's what you have to do. Practice a lot, and that will increase your speed, and it will make sure that when you are doing things faster in the exam, you end up doing less careless errors as well. Doing a lot of practice will help you reduce those careless errors, and just don't get stuck. That's the most important thing that you need to keep in mind. Do not get stuck at a question in the middle of the paper. If you can't figure something out, don't make it an issue of your ego that you have to do it right at that point. It especially happens with those of you who uh, generally do well in maths. You think that no, there can't be something that you cannot figure out. Then you end up messing up the rest of the questions because of that. Just leave it. It's okay. Just attempt the rest of the questions that you do know, making sure that you leave enough time for you to come back to that question that you left, and then you can think about it at the end, and then do as much as you can, and the rest will be taken care of by the threshold. M1 is generally easier than S2 because S2 is a more advanced version for S1. M1 and S1 are generally easier papers. S2 is relatively more difficult, but it really depends. If you are not someone who's doing physics, then it does not really make sense to do M1 generally. For some reason in Pakistan, a lot of schools don't offer S2. But if you are not studying physics and not studying sciences, you should probably take up S2 because that will be helpful for you in your university later on as well. Not always. It's not always that if the number of marks is, if you have more number of marks, the question is going to be more difficult. Sometimes you get uh, high value questions that are easier as well. You should definitely not leave them for the end of the paper. Uh, Mostly kinematics questions are going to be the trickiest. Okay, the rest of the questions in mechanics, uh, there isn't really much that they can do to increase the difficulty level by a lot. Kinematics is what is going to cause problems mostly. So I would recommend generally leave the kinematics question if it looks difficult. That's also not always going to be the case. The equation questions, the differentiation integration questions, they are generally easier. But these questions where you have multiple particles, or one particle that has multiple parts of its journey, they tend to be a bit complicated and take a bit of time as well. So these questions you can probably leave for the end. But if it seems to be an easier question, just do it at that point, because you would want to also make sure that if it's an easy question and carries a lot of marks, you need to make sure that you get to all of those marks. And leaving that question for the end would actually uh, be risky, that you would end up losing those easy marks. Yeah, okay. Now, let's have a look at a work energy power question that you're saying. May-June 2024, paper 4, variant 2, question number 6. Isn't that something that we just did a couple of days ago? May-June 24, paper 4, 2. Okay, let me have a look at that. May-June 2024, question number 6. Oh, Okay. Umar, can I share with you a video for this? Can I share with you a video for this? We just did this a couple of days ago in another class. I'll share a video for this. Okay, it's going to take some time. You can have a look at that video. And if you have any question on that, we can discuss that then. Yeah. Okay. So I'll share the recording of that session with you. Okay. All right. So these were relatively more difficult questions on momentum. You won't find many other questions that are very difficult. There will be a couple of other in recent papers which will be very similar to this, where you have kinematics in some part, momentum in another part. Let me actually show you another. March 2024. This was another very, very tricky question. Again, very similar. You have kinematics in the first part until there is some collision. And then something happens after collision as well. So you use kinematics before collision, and then for collision you apply conservation of momentum, and then after the collision you have a coalesced particle that moves to the ground, and you have to use kinematics again for that. And this was also another very lengthy question. So these questions tend to be difficult. This is a pattern in the recent papers: kinematics and momentum. Kinematics and momentum. When these two come together, that's a deadly combination. You would want to leave that for the very end. Definitely don't do this question in the middle. Okay. All right. Okay, so that concludes our M1 course then. What we will do is we can have another session at some point. So maybe closer to the exam, where if you have any more questions, so some of you have not been able to attempt the worksheets alongside, some of you have not been able to attempt all the questions from the worksheets yet, or you may be doing more practice from recent past papers as well later on. So we might be able to do another session at some point in which if you have any other random questions from any of the topics, we could discuss them at that point. And of course, you can keep sending your messages, keep sending your questions on the WhatsApp group as well. Try to help each other out. Some of you have been doing that. I would appreciate if more of you can do that as well. When you explain something to somebody else, it actually helps your own concepts as well. So I would really recommend that you try to help each other out, and you can still keep sending questions on the WhatsApp, and that should be helpful, inshallah. Okay. All right. Okay. So if you guys have more questions, we could have another session. Okay, we could have another session to discuss those questions. You can also post these in the WhatsApp group. What I'll do is I'll share videos for these as well. Okay. So I might have these solved somewhere. November 23 paper 4 variant 1. What I'll do is I'll show you the solution. You can take a snapshot right now. And then if you have questions on that, you can ask me. November 23 paper 4.1. Okay, let me just look for that quickly. November 23. November 23 paper 4.1. Question number 4. Okay, maybe you can take a picture of this, try to understand it. Try to understand it. And if you don't get something, we could discuss it then. This is the one, right? Yes, recordings will be available of this crash course until October, November 2025, inshallah. Yeah, so until the November session, you'll have recordings available, okay? Have you taken a picture of this? Okay, this is the second page. Third question. Take a snapshot of this as well. It doesn't look that difficult, does it? Done? Take a picture of this? Okay. The other question that you were asking about that is question 7, March 23. Okay. March 23, question March 23. That's not here. That should be somewhere here. March 23, question number 7. Is it this one? Okay, maybe you can take a snapshot of this. And then if you don't understand something, could discuss it then. So there's no driving force here, there's no resistance. You can I'm just using conservation of momentum. If you want to use that work energy principle, that should also work. Have you taken a snapshot of this? Yes? Okay. Oh, that's a big question. We might, this is March 23, right? We might actually do this paper in those sessions as well, although its turn is not going to come soon, Abhi. Maybe by the end of this month. Done with this as well? And then, oh, this looks like a scary person as well. What I'll do is show you this first. Take a snapshot of this. And the last part of the journey. Okay, we will definitely be doing this paper. Okay, please remind me about this. This is one paper that we should definitely be doing in the last paper, session 6.67. Okay, are you done taking snapshots? Okay, good. So you can have a look at this. If you don't understand something, let me know. I'll explain that. But that's it for now. I will see you guys again. If you guys have any problems, you can keep sending them on the WhatsApp group. Help each other out. And all the best for your exams. I'll see you again at a later point. Inshallah, as I said, we could have another session once you're done with the worksheets, hopefully in a couple of weeks, and you still have any problems. We could have a longer session at some point in which we could discuss all the questions that you might have remaining. All right, I hope this course was helpful, and I'll see you again at a later time. All the best for your exams. Allah Hafiz. Glad to know that. You're welcome. You guys are welcome. Thank you. Allah Hafiz. Thank you. Thank you so much. Happy to know that this was helpful. For the video, yes, Umar, please leave me a message on the group. Leave a message on the group, and I'll share that video with you, okay? Make sure to leave a message because otherwise I will forget. There's so much going on. And I'll share that later, okay? Allah Hafiz.